Welcome back. We're going to continue our discussion of integrals now by talking about Riemann sums. This is the second of the 5 topics, and it's very related to area under a curve. By the end of this video, you should be able to use Riemann sum notation to express a rectangular approximation. In other words, your homework quiz tomorrow is going to be a lot of questions about the notation. Let's get started. So you should remember sum notation from pre-calculus, but let me just refresh you a little bit. This is a sum, this notation. This symbol is a sigma, which is a capital Greek letter S, and it just means sum. The way we read this is the sum from 1 to n, sometimes n will be a number, of f of k. N represents the total number of terms we're going to add, so you would see 1, 2, 3, all the way up to n terms. And f of k is a formula or a pattern for how to find each of these terms. If you feel rusty on sum notation, I recommend taking a minute to look at this slide for a second, maybe even to Google it or look back at some old notes. If you're comfortable, let's just check that you're fluent in this with 2 little examples. For each of these examples, the first and the second sum, I want you to rewrite this expression using sum notation. For the first example, notice that these numbers are the same thing as 1 times 2, 2 times 2, 3 times 2, etc. And for the second one, I actually have a typo. So pretend like this says x to the 6th, and this says x to the 7th. Somehow I messed up my numbers. Again, your job is to write these in sum notation. So hopefully that wasn't too hard. These are the way that I wrote my answer. And whenever you do sum notation, there's 2 really good quick checks that you can do to make sure you have this done well. First of all, double check that your number of terms is correct. There are 5 terms being added. That should match the number of terms from k all the way up to n. And then also just double check that this formula works. In other words, if I plug in 1 to this formula, 2 times 1, I should get the first number. If I plug in 5 to this formula, 2 times 5, I should get this number. All looks good up front. For number 2, there's 2 ways you could write it, and a lot of people tend to be confused with this k, so I'll try and clarify before we go any farther. First of all, you notice that what's changing each term is the exponent, and so since I see that there are 6 terms, I set up my first sum from 1 to 6, but then since the first exponent is 2, I assign the formula k plus 1 to denote the exponent. Alternately, if you didn't want to mess around with the k plus 1, you could have started your sum at 2 and gone up to 7. That's fine, that's still 6 terms. And then you could just have the formula x to the k. Regardless of which format you use, it's really important that you understand that k goes in the formula, whereas n is a number. Again, k is part of your formula. Okay, so why are we talking about any of this? We've been studying area, and the idea we've started with is the idea that if we really want the area under the curve, we can approximate it using some rectangles. In practice, this is what the work looks like. And it was a little different depending on whether we're talking about LRAM or RRAM or MRAM. But look at each of these. And think about the structure of each of them. And then make an educated guess. Why do you think we started by reviewing sigma notation? Exactly. These are all sums. So sigma notation, which is basically a shortcut for writing sums, is actually really closely related to LRAM, MRAM, and RRAM, because each of these is basically just a list of things being added together. And especially since we ended the video yesterday talking about how higher ends gave more accurate approximations, sigma notation could be really helpful, especially when we want to add up a lot of rectangles to get a more accurate area. Good thing there's a way to do that. So this is what Riemann sums are. A Riemann sum is when you use sigma notation to represent a rectangular approximation. I want to emphasize that the idea behind a Riemann sum you already understand. I'm just teaching you a new way to write what you already understand. Let's take apart the notation. This is what every Riemann sum looks like. I is just a term that tells you what to do for each rectangle. You don't need to think about the meaning of I. N has a meaning though. N is essentially the number of rectangles we're going to be adding up. In this case, 1, 2, 3, 4, 5, 6, 7. So it would be from 1 to 7. F, of course, is the function in question. Looks like a cubic here. But f of xi altogether represents the height of each rectangle. In this case, we're looking at a left-hand approximation. So the fourth rectangle has a height of f of x3 or f of x4, depending on if you start with 1 or 0 here. This delta x represents a change along the x-axis, which is really just the width of each rectangle. It's the distance between the 2 points, and you already know how to calculate that generally. The trickiest thing when you're getting used to Riemann sum notation, I think, is just understanding what the xi's are. Remember, I is just a number that we're using in order to communicate about the pattern that the sum is summing. So it's like saying, what should I use as my x value to find the height of the first rectangle? And you've already been making that calculation without knowing it. When you choose to use either the left-hand x value or the right-hand x value, you're basically just choosing what x of 1 is going to be, or what x2 is going to be. When you make that choice, we're going to use this point and this point and this point. What you're doing is creating a partition which divides the interval. This partition is the list of the x values that you're going to add. Again, if you want to compare this notation to the Riemann sum here, we could take this first left-hand Riemann approximation, and we would say the x values that I used are 1 and 2 and 3 and 4. So that's my partition, x1, x2, x3, and x4. And if I wanted to write this in sum notation, I would say, well, I'm adding up from the first to the fourth of 1, which is our delta x, times f of that x value, f of xi. And again, xi just tells me where to find each of my x values. Okay, let's get some real practice with this. For each of the 3 examples on the screen, your job is going to be to write a Riemann sum, which represents the quantity. I'll do example A with you. We're asked to find the area under this curve. We're given the interval, and we're told to use LRAM with n equals 4. Without necessarily graphing this function, you should be able to visualize approximately what this means. There's some parabola, there's an interval, and we're supposed to find 4 rectangles that approximate its area. If you are struggling with rectangular approximation, it's a fine idea to use the online tool to visualize it specifically. But as you get better at this, you should be able to interpret what this means and picture those 4 rectangles without necessarily graphing it. Certainly it will save you a lot of time if you don't graph it, but you just start thinking about what the addition should look like. For example, you know that if n equals 4, we're going to end up adding 4 terms, which means the sum is going to have terms from 1 to 4. Now, what is it exactly that we're going to be adding up? What are those 4 things? Each one is essentially a height times a width. Well, in order to specify the Riemann sum for this function, we need to write a more precise explanation of height and width. Width is pretty easy. Width, which is the same thing as delta x in the Riemann sum notation, is the b value minus the a value divided by the number of rectangles. This is how wide each rectangle should be. Height is a little bit more complicated. When we've done Riemann sums in the past, we found the height of those rectangles by plugging in some x value. In the notation on the previous slide, xi represented that idea of some x value. But if we're going to write a precise formula, we actually need to tell whoever's reading this what the x values are going to be. And the way that you do that is by creating something called a partition. A partition is just a list, and it's a list of x values, the x values that you want to use in your sum. You start the list using curly brackets, and you're just going to list the numbers in order. This is where it might help you to sketch a little number line. I'm going to model doing it without a number line, but you can also refer back to this image to figure out what the x values are. Since we know we're doing a left-hand approximation, I know that the first x value for the first rectangle should be the same thing as the a value, the first number in the interval, and that was -1. After the first rectangle, the second rectangle starts 1.75 units later. In other words, if I add 1.75 to -1, I get the next intercept, or the start of the next interval. When I do that addition, it turns out that the next interval starts at 0.075. If I repeat this process, the next rectangle would start 1.75 units later, which is 2.5, and the fourth and final rectangle will start at 4.25. This should feel pretty familiar. This process of finding those x values is the same work that you've been doing this whole last couple of days. If you don't understand where these numbers are from, I recommend that you go back to sketching, and when you sketch your rectangles, look at where your rectangles start and end, and then think about being careful. If we're using the left-hand approximation, use the left side x value. If we're doing the right-hand approximation, use the right side value. Midpoint, you know what to do. Okay, last step to write your finalized Riemann sum is to put this all together. We want to write a sum notation that has actual algebraic expressions here. Obviously, we start with 1 to 4. And then instead of just writing f of xi, we're going to use the formula given. If the function f takes the x value, squares it, and then multiplies times 3, the height is going to be 3 times each of these x values squared. Now, the final piece, normally we would write as our delta x. In this case, it's 1.75. For reasons connected to what we're going to do next, it would also be acceptable just to leave this as delta x, since we've already written what it is up top. And again, the reason for that will come up as we go farther in integrals. This is your final answer, but the partition is part of your answer, so make sure that you've clearly labeled your partition. Again, we started with sum notation, we determined the width, we figured out the partition, the x values that I should use for the heights, and in order to do that I had to think about what left-hand approximation means and what n equals 4 meant. Try to repeat this process for the last two. B looked like this. This would have been the final sum, but the partition is part of the answer as well. And C would have been like this. Okay, now that we've done all this messy notation stuff, let's take a moment to remember some of the big ideas. A couple days ago when we started this unit, we tried to estimate the area under this curve. And we did it using n equals 5, then n equals 10, and n equals 50, and using technology. Now we've got Riemann notation, so we would have an easier time writing out what these sums are. But it's still pretty annoying to have to do these long sums just to get an estimate. What could we do to find the true exact area? If higher ends give better estimates, what would the real answer be? Okay, I'm really excited to read what you wrote for that, because this is a huge idea, and I bet somebody came up with it. The big reveal for this unit is, in order to calculate the exact area under the curve, we just need to take a limit of the Riemann sums. In other words, a limit of the area estimate as we have more and more and more and more rectangles. Because you've already seen, the more rectangles we use, the better the approximation. And that idea of taking more and seeing what happens is exactly the idea of a limit. Now notice that the limit, the terms of the limit is n represents the number of rectangles, so there's still some ambiguity here about what the xi's are. But the idea intuitively should make sense. And actually, there's an even bigger reveal, because that's what an integral is. This is what an integral looks like. It's read the integral from a to b, and an integral is the same thing as the exact area under the curve, which is basically just the limit of the rectangular approximations. We use a Riemann sum to represent them. So cool. That's it for today, actually. You should be able to express rectangular approximations in Riemann sum notation, and I'll see you in class.